Hi everyone, welcome to the Machine Learning Meetup. Thanks for coming. Today we're going to hear from Shikun from Imperial College, who's going to be speaking for about 40 minutes about Prismer, a new multimodal large language model. And after that, we'll have a 20-minute discussion, which is going to be led by Zora Wang, who's a master's student at Carnegie Mellon University. And we're hoping for lots of participation from you, the audience, as usual. So please add your questions into the QA function as usual. Just a reminder not to use the chat function, use the QA function to put your questions in. And that way Zora will be able to see them and ask them when we come to the QA section. So put your hand up as well if you want to ask your question as usual. Otherwise, Zora will ask your question for you. Yeah, I think there's nothing else for me really to say. I'm Martin Goodson. I'm from the organizers, Evolution AI, but now I'm going to hand over to Shikun.
All right. So just to have a quick text, is it my sound working okay?
Yeah.
All right. Okay. Thanks, Martin, for the introduction, and thanks everyone for being here watching my presentation. Okay, let's get started. Today, I'm going to share our work on advancing vision language models with multimodal expert, which is also called the Prismer model. And this is my internship project, collaborate with the NVIDIA machine learning team. Okay. Let's first have an overview of the progress in advancing state-of-the-art vision language models. In the early days, most vision language models are built with BERT-like architecture and have a pretty complicated training objective, like with a combination of multiple losses, in order to align the limited image text parent data into a unified representation. We can see some models such as Unimol or VLT5, they have like even 6 training losses, which are really complicated. Well, particularly considering if we need to tune the task weighting of each training loss as well in order to achieve optimal performance. And similar to BERT-based architecture proposed in language modeling, they cannot do open-ended reasoning and with predictions bounded by the training dataset. And later on, particularly with the success in autoregressive language models like GPT-3, and people started to design generative vision language model in order to do free-form reasoning and consider all vision language reasoning problem as a conditional language generation problem, with the conditions here are images. And training objective is just much simpler, like typically just one autoregressive loss. And inspired by model scaling in language models, we can see a similar trend in scaling vision language models as well, like with more and more compute and training data required to further advance performance. And while scaling language models is already pretty challenging, then scaling vision language model is definitely more difficult because vision language reasoning is a strict superset of language-only reasoning. And at the same time, we noticed that most of these models are very inefficient to train, like models in BERT architecture as well. Like these models are typically trained from scratch or require fine-tuning all parameters on the existing backbones. And in order to effectively scale the models, we then require collecting a lot of image text parent data, which costs like this exponential growth of the training cost. Okay, so considering we already have a lot of great open source models. For example, in Hugging Face, now we have like, it already included like nearly 200K open source models already. And includes a model doing language modeling, some really popular one like OPT and the recent like Lemma and vision understanding network like ResNet, vision transformers, and also a lot of some other specialized task or data set like object detection, depth estimation models as well. So it motivates me thinking like whether we can design vision language models by leveraging these already pre-trained domain-specific experts, such that we can reduce this huge training cost, particularly based on the observation that like many vision language reasoning problems, such as the image captioning and the VQA, they also require the model to be capable of a lot of subtasks, such as fine-grained object recognition, detection, counting, and these very domain-specific specialized skills in order to perform like good multimodal reasoning. And this leads to the design of Prismer to achieve good open-ended vision language reasoning performance which is compared to a lot of state-of-the-art models, but only with a fraction of training cost. And Prismer, as the name suggests, is inspired by the optical prism, and to break a white light into a spectrum of colors. And we here is to decompose a single task reasoning into multiple domain specific reasoning. And in this specific example, if we want to curate a question like what this person is doing, what this person is holding, then we can easily get this answer from the object detection labels. And for more fine-grained information retrieval problem like what's the number of this player, we can then easily get this number from the OCR detection labels. So here we consider multimodal expert knowledge as an auxiliary knowledge to the query RGB image. Well, because clearly not any single expert can do all of the reasoning, because we still require the RGB information and for the very precise information, right? But these expert model can provide useful features fused into a shared representation that can greatly improve the training efficiency. Okay. And this is definitely not the only way to communicate with these multimodal experts. And another line of direction is to directly query these pre-trained expert via in-context language prompts. So we can directly inference these expert models without any further fine-tuning. And two notable works align this direction are like Viper GPT and Visual Chat GPT. And well, interestingly, both of these works, including Prismer, they all submitted to arXiv in March. So it seemed like March has become the birthing month of the large-scale multimodal learning. Okay. And anyway, Viper GPT here performs reasoning by generating Python code, like with large language models like GPT-3. And this generated code just pretty much just decomposed the reasoning problem into some sub-problems, and then curate the corresponding domain experts to solve each problem. For this example, we can say, we can create a question like, does that pancake look brown and round? Then we first have an image detection model to find the pancake, and then using other specialized model to verify whether it's round and whether it's wrong. Okay, and then return the answer. Okay, and Visual Chat GPT does a pretty much similar thing by having even larger flexibility on solving multimodal generation problem, including some control net or stable diffusion into the query model list, and is built on top of ChatGPT, obviously from the title. And we then just need to provide examples and internal correlation among these query experts. And then ChatGPT will just learn how to interact with this model accordingly with natural languages. Okay. And here I present a side-by-side comparison of both directions to hopefully explain this concept better. Okay, in Prisma, which is direction 1, where you focus on learning a unified representation to fuse the knowledge offered from these different expert models. So it requires a bit of model training, but it has some very interesting and useful learning properties like strong robustness of noisy experts. And we have less constraint in terms of the selection of different domain experts, which I will explain further in the later slides. And for the direction of Viper GPT and Visual Chat GPT here, they're both zero-shot methods. So they can easily add as many experts as we want, as long as we just provide their corresponding example, like how to use this model and for different model interactions. And while Prisma is bounded by the expert doing fine-tuning, so it cannot be easily adapted to new and novel experts. Otherwise, this fused representation will be out of training distribution. Okay, and furthermore, in this direction too, they are solving reasoning tasks in a divide and conquer manner. So error will be accumulated. For example, if we want to query a reasoning task to count the number of dogs in the image, and if the dog detection expert predicts an incorrect answer, then this error will be propagated to the later experts. And then there's no way it can return a right answer, as long as there's one expert returns a wrong answer in the loop. So these frameworks will be very sensitive to bad experts and are constrained to a careful selection of experts that are useful for these reasoning tasks. And since both methods, including Prisma, require inference on these expert, a lot of different experts for each query questions. So they are not really efficient in terms of inference time, which are the current, I would say, is the current biggest limitation. Okay, so now let's get into the details of the design of Prismer. So first, let's have a revisit these experts we have included in Prismer. Okay, so in Prismer, we consider 6 modality experts, among which 3 experts, like in the top row here, encoding high-level semantic information, which include the first one here is semantic segmentation and object detection and OCR detection. Okay, and also we have 3 other experts in the bottom row. Here we encode low-level information, which include depth estimation. Here, this is surface normal, and this is edge detection. And we call them these 6 experts as modality experts, as they encode different modality of information. And these 6 experts are frozen and during training, as we only use their corresponding predicted labels for fine-tuning and for other additional training. Okay. And at the same time, we also apply another form of experts, which is the vision-only and the language-only expert, to construct the backbone of our vision language model. So we call them as backbone experts. And then we apply 2 types of parameter-efficient trainable components. One is this expert resampler here, which is to map a varying number of expert tokens into a fixed length of tokens. So here, like the expert knowledge is bounded. And 2, we have this adapters, like in this green little color. And this adapter is to link and connect like the multimodal labels as well as the vision and the language part of Prisma into a unified network. So during training, we only apply like very simple single objective, which is this conditional autoregressive language modeling laws. And with these backbone experts are also frozen. So we only need to train the parameter of these newly introduced layers, which are very lightweight. Okay, so let's have a detailed look of this learnable component. First, we have expert resampler. It is learning a predefined fixed number of latent queries to cross-attend with all multimodal labels from these 6 modality experts. So in other words, it is learning to distill auxiliary knowledge into a fixed number of expert tokens, okay, which can be considered as a form of auxiliary knowledge distillation. So this is motivated by the intuition that there are only limited amount of information including in each image, but we may have unlimited number of domain experts. So if we add more and more experts, we only can bring fewer and fewer information. Okay. And secondly, we have adapters. A lightweight encoder-decoder design, like with residual connection. And we initialize all adapters with near zero weights to approximate the identity function. So the model just is able to smoothly transition from the domain-specific vision-only and language-only backbone to a vision language model during pre-training with paired image text data. Okay. And of course, we have experiment with a lot of other design for Prisma. And here is one representative alternative design that we consider vision features as tunable soft prompts as the major difference compared to our final design. And compared to our final design, it has like this extra output resampler as well to constrain the input image resolution. Though actually this alternative design has a slightly improved performance than our final design, but it needs to sacrifice like significantly in terms of this memory during model training, because now in the language decoder part, the running memory will be quadratically proportional to the number of vision tokens. Okay, but our final design here is only linearly proportional to the number of vision tokens, like due to the use of cross attention. So as we here aim to have an efficient model design, and we eventually settle down this as our final design to further save memory. Okay, and in order to and in addition to our Prisma model, we also introduce another model variant named Prisma Z. So Prisma Z here just solely relies on the power of strong backbone expert, and it is trained without any modality experts. So it's just using RGB image only. And therefore Prisma Z just simplifies the data inference process because it only requires RGB images. like making it very, very efficient and hopefully have a wider range of application. And Prismer is less efficient in data inference because you need to have inference across all of the 6 modality experts, but it will achieve a better performance. Okay, and here Prisma and Prisma Z, they both built on top of a clip-trained vision transformer as the frozen vision encoder, and the Robota as the frozen language decoder. And we did try to use like other popular decoder-only language models like OPT and Bloom, which we thought would be like more suitable for this autoregressive language modeling training, but we did not observe any improvement in terms of final performance. So settle down with Robota in terms of simplicity. Okay. And we experiment with 2 model sizes, base and large, corresponding to the size of our backbone experts. And we can see here the Prisma model is not very large. Like with the trainable parameter is only like 15% of total 1.6 billion network parameter in our large model variant. And this total network parameter have already included a parameter of 6 expert modalities. Okay, and here we can see how Prisma and the Prisma Z's performance compared to other state-of-the-art vision language models. And first of all, we can see both Prisma and Prisma Z here marked as red and orange colors are able to achieve very good performance. So it means that the backbone experts are mainly responsible for good generalization. Well, this is also fits human intuition because these backbone experts were pre-trained with web scale data. And however, we can further improve performance by including these 6 modality experts, which is the performance of the default Prisma model. And specifically in BQA V2 datasets, Prisma perform similarly to GIT with 63 times better in terms of data efficiency. And in image captioning benchmark, like in no-caps dataset, it reaches similar performance to Blip and Lemon models with roughly 10 and 20 times better in terms of data efficiency, respectively. Well, despite the fact that the number of trainable parameter of Prisma is roughly the same and also sometimes smaller, and most of the times smaller than these state-of-the-art models. And also here we represent the model size here as the size of the block. Okay. And additionally, we found out that Prisma is significantly strong in zero-shot generalization, where the model pre-trained by this autoregressive laws can be directly applied to image capturing tasks without any additional fine-tuning. So for example, here we can see Prisma achieves significantly better performance in COCO caption dataset than of the previous state-of-the-art models, and noticeably better than CNVRM on the no-caps datasets, while using like 140 times less training data and 4 times less in network parameter size. Okay. And here are some zero-shot generated example caption in no-caps datasets. And we can clearly see Prisma Large here can generate like better quality captions than the Prisma base, like including some like fine-grained object information like the brand names, like such as that's CK1 in this particular example, like more accurate than this alcohol predicted by Prisma base. And this is also showing that OCR detection expert can be very useful because we can just directly take the predicted text labels from this expert. And similarly, in this example, Prisma Large generate accurate car brand name Mercedes with similar caption quality to the human rated one, like the second one here. A shiny white Mercedes car is on display, which is pretty similar to what Prisma Large predicted. A white Mercedes car is on display at an auto show. Okay, and this is a very interesting example. So we can see here the object detection expert predicts the wrong labels. So it mislabels the pineapples with toothpicks as umbrella class, which I have to say it is a very challenging case here. And this is why it's very important, like in the design pipeline, we only consider expert knowledge as auxiliary knowledge. So the model has to learn a good generalizable representation to include all information and not to overly rely on expert label. So here the Prisma still predicts the right caption knowing this is a pineapple cake, rather than the umbrella. But if we apply the framework like Viper GPT or Visual ChatGPT, then they will fail using if they're using like the same object detection models to do image caption. Okay. And we also evaluate Prismer on ImageNet dataset, like in a few shot setting, and we convert the image classification task into a language modeling problem by mapping each unique category to a template caption, like saying like a photo of like the predicted class name. Okay. And unlike other vision language model like Flamingo in this case, that performs few shot classification like with in context example, like without any gradient updates, we perform a few shot classification with lightweight fine tuning following GIT. So this is more similar to like the standard linear probe setting, like in the standard unsupervised vision representation learning literature. So here we consider like the entire language decoder as an image classifier. And accordingly, we also compare with the few shot linear probe performance of Prismer's original vision backbone, VITB and VITL, for the space and large model respectively. And from the results shown here, we observe that Prisma underperforms GIT and Flamingo, which both have a much stronger vision backbone and are pre-trained with 2 or 3 magnitude more data. However, Prisma still outperforms its original vision backbone, VITB and VITL, by a very large margin, especially in the very few shot learning setting, like particularly like 1 or 2 shot, it can improve performance by nearly 20%. Okay, and this suggests that the Prisma's generalization abilities are enhanced by this multimodal training data and the use of expert labels. And its performance can likely be improved further by using an even stronger vision backbone. And finally, we have done an application study on training Prisma with different kinds of experts. And we have observed some very interesting learning property. And we concluded with 3 different observations. And this experiment is done on VQA V2 dataset. So here, this accuracy just meaning the accuracy of the VQA V2 answer. So higher is better. Okay. So first observation, more experts, better performance. And this is very intuitive because, well, if we include more experts, it will definitely provide a greater diversity of the domain knowledge to include to the model. So it can improve the model further by including more experts. But we also note that the performance of the model eventually plateaus after including a certain number of experts, which suggests that additional modality experts do not provide any extra gains. And this observation also verifies our assumption on like designing expert sampler with a bounded length of tokens. And observation 2, better experts, better performance. So to evaluate the impact of expert quality on Prisma performance, we're sort of designing like a fake bad experts, like by corrupting its predicted labels. And we did this experiments in our depth expert. So we're doing like to replace a certain number of predicted labels with the random noise sample from a uniform distribution. And we can clearly see here the Prisma performance also improves as the quality of the depth experts improves. And this is also very intuitive because, well, better experts provide more accurate domain knowledge. So the model can perceive more accurately. And this is a very useful and important learning property because we only need to train the model once with the predefined experts, and we can just freely swap the experts with a better one to improve the performance without any requirement to like retrain the model. Okay, and finally we have this observation 3, robustness to noisy experts. I think this is the most interesting property here, as we also observe that Prisma maintained the performance even when including expert that predicts pure noise. And this property allows the model to safely include as many experts as we want without degrading the performance, even when the expert is not necessarily informative. Therefore, like Prismer presents like a more effective learning strategy, particularly compared to these zero-shot methods, which are very sensitive to the quality of the experts. Okay, so finally, with any models, Prisma has its own limitations. And here I would just discuss some of the important limitations we have discovered during our research, and also the potential future direction of this work. Okay. First, since we really aim for like training and model parameter efficiency, so we built Prisma on top of like small scale language model. Therefore, it does not have the ability to perform few shot in context prompting, which is like the emergent property in very large language models, such as like the 70B Chichinla model used in Flamingo from DeepMind. Secondly, Prisma can only inference with the exact same type of experts it was trained on. So it has limited adaptability to a different expert, like with a different set of semantic information. And they will lead to a notable performance drop. I think it will be really interesting and important just to study how to freely add or remove expert without requiring any additional training. Okay. And thirdly, better expert selection. So we found out that like not all experts have the same. For example, like segmentation and detection, they may have some redundant semantic information, or even though like detection will also bring the instant information which segmentation model doesn't have. But just adding a single model, the performance brought from a single model definitely will be much smaller if we including like two models. And this is also like an active research area in multitask learning, which was also like my major research interest, like to study the task relationship, like to understand how one task can help the others. Okay. And fourthly, here we only consider vision-based experts as our modality expert. And we treat all task knowledge as like an image-like tensor for simplicity. So there are definitely better ways to represent this expert knowledge, and hopefully just to more effectively encode these modality information. For example, we may consider object detection as a sequence-to-sequence task, like to directly feed spatial information to the language decoder. And this object detection representation as a sequence of coordinate technique is also like adopted in the recent segment anything model from Meta. All right, so for my last slides, I like to especially thank all the open source community to make this project possible. Well, particularly Hugging Face, which generously donates a GPU, so we may run our Prisma demo online freely accessible to the public. As the motivation of the Prisma design is to unify the power of different open source model. So as a return, we also have tried our efforts to convince NVIDIA to make Prisma open source to everyone as well. So please do check our code or demo if you're interested in any more technical details. Okay, so that's all for today, and thanks everyone for listening.
Thanks, Shikun. Thanks for a great talk. So now I'm going to hand over to the audience and to Zora. So Zora is going to conduct the QA section of the event today. Like I said, to those of you in the audience, please add your questions to the QA function. Zora will work through your questions if you get selected. Also, remember to put your hand up if you want to ask your questions yourself. Otherwise, I'm going to hand over to Zora for the QA. Thanks, Zora.
Yeah, thanks. So thanks, Shikun, for the talk. A very interesting work. Yeah, I do have a lot of questions when I was listening to the talk. Yeah. So like the first thing that I'm like most interested is like about the domain experts. It seems like a very efficient way of leveraging like the current community efforts of like all the state-of-the-art models in different like tasks. Yeah. So I'm wondering like, what's your experience when you're selecting this domain experts? Like, how do you select based on their like different skills where like different domains that they're like good at? Can you like explain that?
Okay, I see your question. Yeah, so at the beginning, I thought it would be better just to find as many open source models as possible, because the property of this Prisma is can have it like zero degradation of the performance, even if we have like very bad experts. But later we found out like during implementation, the process of data augmentation on these different expert model will require much longer time than the model training into like one forward pass of the model itself. So it's not efficient in terms of the actual implementation. So later I shrink down just to encode 3 like encoding semantic things and 3 encoding like more like low level vision signals. And also I have to consider whether this domain is very actively being researched in the community. For example, the depth expert is a very good example because we have the Midas expert that is always improving based on a better vision transformer. Like for surface normal, which is less actively being researched, or the quality of the expert would drop on a little bit. So that is also one consideration. I also a little bit hesitated whether we should add this edge detection expert as well, because the model I use is also very little bit outdated. For example, the controller, I think they're just using the Kenny edge, which also works well. Yeah, so these pretty much are my consideration.
Yeah, I think like I personally feel like the group of domain experts they select here is very important. Like they might need to have certain like overlap in their skills so that like they can somehow help each other. But you also, on the other hand, don't want them to be like very similar, playing very overlapping functions, so that like the marginal effort brought by each expert might be not significant enough. But yeah, I guess you have a like very good combination here.
Yeah.
Another.
Sorry, yeah, just to add another point here. So because I thought like the segmentation and the detection expert will bring similar information in terms of semantic labels. So I deliberately choose the model like pre-trained on different data sets. So we hope just to like to spread the labels across more classes. So to bring more generalization, which is also probably one of the good advantage here.
Yeah. I think this is a like really good point that like you by aggregating this domain experts here are actually like aggregating their training data too. So if their training data diverge a lot and covers a lot of different domains, then like the aggregated Prismer model might have better generalization abilities.
Yeah, that's also the point. Yes, I agree.
That's awesome. Yeah. Another question that I have is like I do like a lot of like text, like language model kind of thing. So I'm wondering, like I noticed that all the domain experts here are like mostly like vision based, like the inputs are like the image. But I wonder, do you think it would be also possible to like incorporate other or like experts in other modalities, for example, a text encoder? And would that like make the model stronger, or would that perform better on more tasks?
Yeah, I agree with this. This is also one of our consideration when we design Prisma, to be honest. So at the beginning, I thought including vision-based model, which is very clear and intuitive. What about we can include some other cross-domain model, like single image to mesh, this kind of thing. First of all, I thought this is definitely very good and probably give you a direct, explicit knowledge of understanding these images or understanding these tasks. But the problem is we don't know how to properly include these representation into the model, like in a unified way. For example, the 3D representation is still an active research area in the community. Like we don't know what's the optimal way to represent 3D. Like NERF is one way that being very popular, but point cloud can be also an effective way, right? Or voxel is also another good way. So this was struggling a little bit. So we just focus on vision experts as our main focus, just for simplicity and to understand how these experts work and collaborate with each other. And for the future work, I would really explore some other like more like multi-modal setting, like image to mesh or even mesh to image, and maybe including video, for example, video captioning and text to video with these kind of models as well. Yeah.
Yeah, that sounds like a good future plan. And also agree that I think the current like techniques that for the current developments is still like an open problem on how to effectively aggregate like information from different modalities.
Yeah.
I think your work is already a good start on like aggregating different experts to like for better performance. Yeah. I was like, while you were giving the talk, I was also thinking about like maybe you mentioned Hugging Face. Like I remember the Hugging GPT a few days ago. Like you find there's some like similarity. For example, I think like that their main motivation was like sort of using the additional trainable parameters in their model to serve as a like manipulation of the other, like in your case, experts models. Do you find your like model also performs in a similar way?
I'm not exactly sure the question. You mean how Prismer is performed similar to this like chat Hugging Face GPT model?
Yeah, I can like give more information about that if I remember correctly. If I think they're sort of aggregating different like open source models that are good at different tasks, and then like have a like alternative module, for example, a like ensembler or like a language model to aggregate information from these different models.
Yeah.
And then sort of using like thinking of your design module as a like additional manipulation model for the other domain experts. For example, for these tasks, maybe only one expert is the like most effective one, and then that manipulation model would like choose to rely on that particular expert more, and then to like do that task.
Yeah, I see the point. I think the Hugging Face GPT is more like this direction too, what I talked about as a related work. So it is more doing like query the most suitable open source model in the Hugging Face API and to like sequentially solve a task. Yeah, so this is the design strategy, I would say, is different from Prisma, because the Prisma is all about how to use the different labels or the prediction from the different expert to sort of unify them into a single representation. But the Hugging Face GPT, along with these related work like Viper GPT, there's like how to find the best suitable model such that you can solve the task in a sequential way by just prompting the language model.
Yeah, I see. Yeah, it makes sense. Yeah. Just gonna pause here to see if any questions online. If
Maybe
not,
Zara, I can just come in with another question if it's okay with you. Shikun, I was just going to ask you. You touched on briefly that one of your experts is OCR model.
Yes.
What is? I mean, what's the output of that model, and what's the connection? Could you talk in some bit more detail about how you use that information?
Yeah. So this is one part I was also struggled to decide at the beginning of the development of Prisma, because the OCR directly predict the text. So it makes sense that we can directly feed the text into the language decoder, right? But we later thought that if we just doing this, then we didn't really give this spatial information, like how large the size of the task. So later, yeah, exactly. So later we just to convert everything into an image-like tensor. So in this example, we just predict an image each time W time the number of language embedding, where these little white pixels will be replaced with the text token of 21. So we hope it will give not only the text information, but also like where is this text and how large is this text into the vision model. Does that make sense?
Yeah, so could you just say again what the representation is?
Yeah, so this is similar to the segmentation at the detection model as well. So we pretty much tile the language embedding to the predicted pixel. And here the particular pixel is the bounding box, right? So in this bounding box, every pixel will have the same representation, which is the language embedding of 21. Yeah, and we do that for these classes as well. So these pixel will be the embedding of person, and these pixel will be embedding of
class embedding. Yeah.
Yeah.
And then did you do any detailed ablations to see whether, like, for instance, the OCR expert is actually helping or not?
Yes, I think that is pretty much our final ablation, just showing like if you're adding more and more expert, then the performance will be improved. And we also did some like different combination of the expert, and we showed that it will also improve. It's just the improvement rate in terms of combining different expert will be different. So let's say I found that the most useful expert here is actually depth, which I think the depth will bring you the geometry information of the objects. So it will just easier to reason across the different object class with the geometry. So
I suppose these results, sorry to interrupt, these results are consistent with quite a number of interpretations, and it could be that the OCR expert is really adding a very small benefit, if any benefit at all. And it's also not clear on which images it's having any benefit.
Yeah, so a more concrete ablation should be the combination of any of the 6 modality experts, just to see whether it will show improvement, which will have too much computing or to get the information. That's why you just need to, well, in order to make it more efficiently, like we need to design sort of like a task relationship method to understand which task is being affected by which expert, which I think is really important. For example,
So for this observation 1 chart, this analysis was just on one task, not across all of the tasks that you.
Yeah, that's true. Yeah, because it's just way too expensive to evaluate on all of the tasks. Because this is one ablation, because we have a combination of different architecture design and learning strategies.
Yeah, makes sense.
Yeah.
Okay, thank you. Thanks, Oren.
Yep.
I see there are 2 hands in the QA. So,
okay. I think normally the best way for those of you in the audience is if you can add your question to the QA and also raise your hand so that we can see what your question is going to be, and then we can choose. But for now, I'm just gonna choose randomly because there's no, you haven't added your QA. So yeah, I'm gonna unmute you and allow you to ask your question. But yeah, for the future, I think it's best if people add their questions to the QA and then put their hand up. So Yamuna, you're free to talk now.
Hello.
Hello.
Can you hear me?
Yes.
Hi. So I work more in the mixture of experts space. So this is actually quite interesting to me. My question though is, so from what I understand, you can take pre-trained experts, right?
Yep.
But even given that each of them is a vision expert, but they still have different outputs, right? They have, each of them is doing a different task, so to speak.
Yeah.
So, so how do you combine that then? How do you decide how to combine it for each problem?
Okay, so for this particular example, all of the experts, they are like vision-based experts. So they will take the RGB images and will predict all of these different labels, right? And these labels will be as like a 3-dimensional tensor. It's the image height times image weight times the embedding. But the embedding will be different. Like the depth is 1, right? Because it just like you can consider as a grayscale image, and the surface normal 3. And the segmentation, object detection, and OCR detection, they are all the size of the language embedding, because we directly tie the language embedding for each corresponding pixels of each class.
Right.
And yeah, and then we convert them into a sequence of tokens by a domain-specific petrified layer. And we design each petrified layer for each domain, but pretty much they have the similar structure, just having like a 3x3 convolution and taking the input channel and then map to the matched final embedding, and then we sort of linearize them into a sequence, like a sequence of token, and we concatenate them into the expert sampler and then distill them into a smaller sequence of tokens.
But does this mean that for each application, you would have to design this part of it very specifically for each application?
Not for each application, but for each domain expert. But we assume the domain expert will be fixed during inference.
Okay, but then if you decide that you have another domain expert that is could add to this, how would that work then?
And then we need to add another petrified layer and to feed them into the expert sampler. But here, because the expert sampler always outputs a fixed number of tokens, so the inference time will not be increased. So that's the good part.
Okay, but you would have to retrain it.
Yes, we have to retrain it, or maybe a little bit fine tuning, I would say.
Okay, so because you could keep all the other, I see, you could also keep all the other pretty much fixed,
Yes.
and then train, I see, just fine tune some of it.
Yeah,
okay.
You just need to train the module such that to convert the new expert labels into a sequence of tokens.
Okay, and from when you say multimodal, are you implying that the inputs and outputs are different? Is that why you say it's multimodal?
Yeah, or we can say it can reason across different modality of information.
Okay, but it's not like I think Zora was asking how, if you, for example, if you had a text expert and you had an image expert, how would you combine them? I mean, if it's truly multimodal in the sense of you're learning from two different sets of data, right? So in that case, would it work, or you'll have to design how you handle the outputs of each of them, each of the experts, I guess?
I'm not exactly following your question.
So say, for example, if you have an expert, which is a language model-based expert, and then you have the image-based expert. So if you want to, sort of combine like tags with images, right? And you want to, have a sort of a classification based on the combined information from text and image, right?
Yeah, okay, I see your point.
Yeah,
so in that case, possibly that these expert information can be directly added to the language decoder. So
okay.
It depends on how we design the expert, how we design to represent this expert knowledge, which I think will be an important future work.
Okay.
But we call this multimodal as meaning we encode different modality of the information into a unified network.
Okay, so since yours is
sorry,
go. Okay, sorry. Yeah, okay. I should go on. Okay, thank you. Yeah, thank you. Yeah.
Thanks so much. So Zora, did you want to ask a question, or should we go to Shaswa?
I do have a quick clarification question, maybe. I'm just wondering, like, are you taking each domain experts and like transfer their outputs to like a output space of the same size and like combine different experts together?
Yeah, this is what we did. Yeah.
Yeah, because like when I was like talking about mixture of experts, I was also thinking about like model soups, that series kind of work. Yeah, basically they're just like the approach is very simple, but like surprisingly works. They just add like multiple outputs together, and that will give them like a good result on like the aggregated tasks. So like I guess I see a similarity here, that you're also like aggregating to transform the expert outputs together to aggregate their efforts.
Yeah, model soup is like a model sampling technique. It's not like adding outputs, but also adding the network weights, if I understand it correctly. But here it's more like aggregating the knowledge predicted from each expert. So the design of the expert can be different. But in model soup, that the design of the model has to be the same in order to aggregate them into the same network. So yeah, they have some similarity, but yeah, the approach we aggregate the network is slightly different.
Yeah, I guess the design here allows more flexible structures in the different domains. Yeah. Cool.
Okay.
Do you want to call another?
Yeah, sure. We can go to Shaswa. And like I said before, can I encourage the audience members to add your questions to the QA, so that we can see your question before you raise your hand? That would be really helpful. But right now I'm going to go to Shaswa. So Shaswa, you can talk now.
Thanks very much, Martin. My question is a bit complicated, so it would have taken me a bit of time. And yeah, just end of the day is a bit tiring, so just lazy, that's all. So if you don't mind me asking you to go to that slide with the performance bars that you had probably toward the end. Yeah, toward the end. One more, maybe a couple more. Yeah, this one.
Okay.
So it's really interesting, and I was just wondering. So, say for example, take the one with the 2 experts or the 4 experts.
Yeah.
That you have in there.
Yeah.
So when you say 72.79, let's say for example, performance or accuracy, does that mean on around in about 100 times, 72 times it got it right? I don't exactly know what's the actual error here that's measured, but it doesn't matter. I'm just wondering that let's say you have different combinations of these 4 experts. By the way, when you say +4, does that mean whatever you had the RGB and +4 more? Is that
+4 more? Yes.
Cool. Okay, so let's just say we have a combination of 3 of them.
Yeah.
And we have multiple combinations of these 3. So
yeah.
1, 2, and 4, 1, 3, and 4, 2, 3, and 4. The result of those 3, are they always going to be less than 4 of them together?
Not exactly. I think that this is a similar question that Martin had as well. Just like how we decide like the optimal combination of the expert, like, or how we know then one expert can improve the performance like compared to the other.
Okay, maybe I'm just re-asking the same question.
Yeah.
I'm stupid.
I think
okay.
Yeah, I think it is just way too expensive to find the optimal combination of the 6, because then we would have to do like 6 choose n with the summation of n from 1 to 5, right? So
right, okay.
Yeah, so this is nearly impossible, which is another important research question in multitask learning, like study the task relationship.
You could just add each task. You could add each expert by itself and see what happened. That would be the first thing to do. That's like 6 experiments.
Yeah.
Okay. Because what I'm thinking is there is some sort of a even higher level of context awareness is kind of interesting. So for example, for the image that you have with the baseball player, maybe there are some experts that are doing better there, but then a hyper sort of context learner that would say, okay, for this current, for example, let's say if it's looking at a video and multiple images coming through, the video doesn't just go from one scene to another scene to another scene every second. So it has some context. And I would say probably learning that context and in that, say, section, that scene of, let's say, whatever it usually goes from 5 seconds to probably half an hour or so in one scene. It would probably increase the performance by quite a lot by knowing which experts to give more attention to or weight those experts more than the others.
Yeah, I think that is the answer from the observation 3, because we found out that using this training strategy, you adding more expert would not affect the performance. So we can just safely to add as many experts we want. But I know if we really consider the inference efficiency, then I agree. Then if we know then which expert will help the most, then we can just inference by that number of experts. So that will really improve the efficiency, which I think will be another important direction as well. Like again, I think that's the problem of to understand task relationship in the observed learning setting.
Cool. Thank you very much.
Yep. Thank you.
Yeah, I think there's also a very similar question, the QA, have you considered using a gate to combine the experts, basically choosing when to or not to use some experts in your experiments? But I agree with that. I think the observation 3 also supports that if you can prove that even adding some experts will not like degrade the performance, and it's like the safest option to like combine like the 6 of them together and like do not have to deliberately choose. And also I think it also has a benefit of like flexibility that sometimes like domain experts, not like model domain experts, like research experts, that we may not know like which experts would contribute to what task very clearly. So that also gives extra flexibility, I guess.
Yeah, so I also thinking maybe it's also important to have like the verification of interpretability, like when we inference each query answer or each query question, that whether we can have this attention mask to knowing like which expert is helping the most in order to determine the final prediction. But I found that, well, particularly in Prismer design, it's a little bit hard to do that because we have 2 levels of interaction. One, the expert tokens, they interact with each other in the expert resampler. So the final predicted expert tokens, they're distilled. So there's no clear correspondence like which token is corresponding to which experts. And second, the expert token will also be correlated with the image token. So the image token is learning with the expert tokens as well. So they're helping each other. So the interpretability will be harder to get in terms of like the mask, like to have a clear relationship, like generating this task, generating the next token is based on that particular experts. But I think it will be important to know, we'll possibly like using some other gradient technique just to understand like which expert is helping, which token would be interesting.
Yeah. I'm wondering, like, so far we're only talking about like the mutual benefit of different experts to each other. Wonder, have you like observed any like, for example, contradictories in the knowledge that each domain experts learned? Like, if like, would there be contradictory knowledge, and if so, how could you deal with that?
So you mean like, for example, we still have 2 depth expert, but one predicting a different depth from the other expert, something like that scenario, I would say, is it?
Yeah, or say for example, we have to like I don't exactly know the 2 names of your first experts here, but say if they're trained on different data sets and they're like predicting different on different regions, would that cause like a contradictory thing?
I think this is similar to this failure case I presented here. So for example, the object detection expert, they predict a wrong label. They predict these objects as umbrella, which is incorrect, and contradictory to the segmentation expert, which predict this as a cake, right? So that's why I think it's important just to consider these expert knowledge as auxiliary knowledge. We still require the reasoning from the RGB information. But if we have some accurate auxiliary knowledge, it definitely will improve performance and improve training efficiency. But even if we don't have these accurate experts, we can just using the RGB information just do the reasoning tasks.
Great. Thanks so much, Zora. I think unless you have any more questions, I think we're out of time. So thanks once again, Shikun. Fantastic talk, really interesting work. I really love this session. And thanks so much, Zora, for conducting the Q&A, and thanks to the audience for coming. As usual, the talk is recorded. It's going to be on our YouTube channel. You can just Google London Machine Learning Meetup YouTube. Please subscribe so you get the alerts when the videos are uploaded, and we'll see you again next time. I think actually next time we're going to do it live. We're going to have an in-person event in London. So watch out for the notifications about that.
Yeah, that would be great. Okay, thank you.
Thanks again. See you guys. Bye.
See you.